Okay, so my talk will begin with maybe it'll be a bit introductory, maybe to Hirako's talk. But so let's begin with G, a reductive group, V, a representation, and I'll also make use of a character of my group, chi, G to C star. So associated to this data, we have two spaces, the Higgs branch. So the Higgs branch is defined as follows. You take the cotangent bundle in V and consider the Hamiltonian reduction of this cotangent bundle at the GIT parameter chi by the group G. So you take the zero level of the moment map and then take the projective GIT quotient at chi by G. That's a Higgs branch. And there's also the Coulomb branch, whose definition was, I guess, originally given by physicists, and then a mathematical definition of the Coulomb branch was given just a few years ago by BFN, Braverman-Finkelberg-Nakajima, in case you missed it. So I will get to that definition shortly, but I just wanted to give a couple of examples. So there's two classes of examples which will be most important for me. The first example when G is a torus. In this case, the Higgs branch is called a hypertoric variety. It has lots of beautiful combinatorial structure. And the Coulomb branch is also a hypertoric variety. And it's in fact what's called the Gale dual hypertoric variety. Maybe I should have actually said from the very beginning, these two spaces are sometimes called, the relationship between this Higgs branch and this Coulomb branch is often called a symplectic dual. These two spaces are called symplectic dual. And in good cases, if something appears as a Higgs branch and the Coulomb branch, and then you find out that the same space can be a Higgs branch, then the Higgs and the Coulomb will switch in good cases. So a sub-example of this example, just to show you how we're doing, we could take, for example, C star acting on Cn just by scaling, and chi just be the identity, and then the Higgs branch will be the cotangent bundle of projective space, and the Coulomb branch will be C2 mod C mod n. Oh, in my talk, this Higgs branch will always be defined using this projective DI quotient, so it will typically be smooth, and this Coulomb branch will always be affine. Of course, you could consider an affine version here, you could consider resolution here, but just for simplicity, I'll think of it like this. So that's one simple class of examples. Another important example is when GV comes from a framed quiver. So let me explain what I mean by that. So we fix a quiver. Usually, I mean just no loops and maybe only most one arrow between two vertices. And I have a framing of my quiver. So I put in round circles the gauge vertices, and in square brackets this kind of framing vertices. So the V associated to this quiver is hom C, C2, direct sum hom C2, C3, direct sum hom C3, C4. And the group associated to this quiver is a product of the gauge groups here. So GL1 cross GL2 cross GL3. And it acts on this vector space V. I said that you should act on V. It acts on V just in the usual way. And in this example, well, in general, sorry, maybe I'll say, yeah, okay. In general, when G and V comes from a frame quiver, this Higgs branch is a Nakajima quiver variety. Quiver variety. And the Coulomb branch, sorry, I was getting a little ahead of myself. Okay. In general, in the quiver case, the Higgs branch is a Nakajima quiver variety. And the Coulomb branch is affine Grassmannian slice. Or generalized affine Grassmannian slice. Associated to the group G, I'll call it GQ, this quiver will be called Q, associated to the group GQ, the group whose thinking diagram. Q. And of course, and this, yeah, just the circles part. And so in this case, for example, this GQ is SL3, SL4. So Hiraku talked about the generalization of this in the case where we have where this GQ is a symmetrizable Katsumani group. Okay. Oh, finally, just in this example, if this happened to be our quiver, and so this was our G and this was our V, in fact, happens to be in this case both the Higgs branch and the Coulomb branch are the cotangent bundle of the flags in C3, C4. Although technically, so I guess because of my definition of thinking of the Coulomb branch always as an affine thing, the Coulomb branch will just be the nilpotent cone of SL4. Okay, so there you have some examples. So I've defined Higgs branch, and I haven't defined Coulomb branch, but I gave a couple of examples of Coulomb branch, and now I'm going to define Coulomb branch. So the definition of Coulomb branch is a little complicated. So it proceeds, let me just, a rough summary. So you start with your G and V. You produce a kind of complicated space called RGV. And then you consider the homology, equivariant homology of this RGV. And this thing will be an algebra. And then you take spec of this algebra. Okay, so it's a multi-step construction. So this will be the Coulomb branch. And this is a complicated space. Okay, so more precisely, we'll need to start by thinking about the affine Grassmannian of the group G. So the affine Grassmannian of the group G, by definition, is G over Laurent series modulo G over power series, and has a moduli interpretation as it pairs P phi, where P is a principal G bundle on a disk, V and phi is a trivialization of P on the punctured disk. Okay. So this space RGV that we're going to end up taking its homology of to make our Coulomb branch algebra is going to be built on this affine Grassmannian as follows. We consider pairs G, V, where G is an element in this affine Grassmannian. So, and V is an element in the vector space V. So the vector space V that enters now. So it's an element in the vector space V, but over tensored with Taylor series, tensored with power series. And we also have the condition that V also lies in this space. So this G, this G guy lives in G of Laurent series. So it acts on V over Laurent series, and it takes this lattice, V over power series, to some other space, some other lattice. And we want V to lie in both lattices. It has a moduli interpretation. There's P phi S. So P and phi are as here. And S here is a section of the associated vector bundle, V associated to P over the disk. Sorry. I'll just write it out. The section of associated vector bundle VP on D, such that if we take this section and we compose it with phi, then we'll get a section, or maybe precompose it. I don't know which way to go. Anyway. Whatever. Maybe inverse, whatever. That this thing extends, so this thing will now be a section of the trivial bundle, and we want this to extend over D. So a priori, because the trivialization is only defined on the puncture disk, this S will only become, after applying this phi inverse, will become a section of the trivial bundle over the puncture disk, and I want it to extend over the whole disk. That's the same as this thing.
So, what is the dependence on the character of the group G?
Oh, not yet. None. The character will come in later. I just wanted to fix it at the beginning because it's kind of useful for my purposes. And the space RGV has an action of G of power series, just coming from its usual action on the affine Grassmannian and also acting on this vector V. And then we formed the homology. And that thing will be called the Coulomb branch algebra, AGV, or maybe more precisely A0, and I'll use AGV for the deformed version, so where we take also the star.
We want it to be precise. Is it really G and V in brackets here? So it's equivalent classes of pairs of G and V rather than...
No. Sorry?
I mean, in your original definition of RGV.
It's like this.
But V is in something where it doesn't depend on the choice of the representative G.
No, it doesn't, because if you change the representative by the left multiplication, it will leave this thing invariant.
Oh, I see.
So it doesn't change the choice of representative. It's just like in the usual definition of Steinberg variety.
Oh, all right.
Or in the potential model of the Flag variety or something. Okay. So one word of warning, that this homology here is not quite an ordinary homology. It's defined using the cohomology of some renormalized dualizing sheaf. Probably the best way to think of it is that, so so this RGV maps to this affine Grassmannian, of course. And this thing is infinite dimensional, and the fibers of this map are also infinite dimensional. So there's two kind of infinite dimensionals going on. But the way this homology works is we consider cycles which are finite dimensional along the base and kind of finite codimensional in the fibers. So typical element here, we'd take some subvariety here and take its preimage here. Or something.
But it's also not usual homology for a different reason. Even for finite dimensional, will still not be the usual homology. It's the Braverman homology.
Oh, okay, that's true.
The thing is singular.
That's true. Okay, it's also true because it's Braverman.
And because it's not compact as well.
Yeah. Yeah.
Right. It's not
compact.
It's not compact and not smooth. So.
Yeah. That's true.
It's more important. It's not smooth and something. It's not compact.
Well, homology and Braverman homology coincide. The space is compact. It's not the. Okay. So. There it is. And sorry, of course, the reference for this definition is the paper of Braverman-Finkelberg-Nakajima. Okay, so maybe I just say this. Here, BFN. So one would be if G is a torus, then the space you get this way is Coulomb. So the Coulomb branch, I didn't say it maybe explicitly, the Coulomb branch MC GV is the spec of this algebra A0. So if G is a torus, then this MC GV is the dual hypertoric variety. First point. The second point, if G, GV comes from a quiver, then this MC GV is isomorphic to this W lambda mu, this generalized affine Grassmannian slice. Where, maybe a word on the notation, so although it's sort of appeared in Hirakawa's tag too, but just in case. So this lambda is directly related to the framing, and lambda minus mu is, you can write as the sum of ni alpha I, and these are the dimensions of the gauge vertices. And this is the affine, generalized affine Grassmannian slice for the group whose the Dinkin diagram underlies our quiver. Okay, so this is a background. Any questions on all that? Okay, so the subject of our work is the following question. So can we use can we define modules for these algebras? Using kind of Springer theory.
Do you want modules for GV or for its quantization?
Both, but in my notation today, I'm actually using AG for the quantization, and I'm using A0 for the non-quantized version. Sorry. Yeah. Maybe before proceeding, let me just note that we have some very familiar-looking algebras which show up this way. So maybe I could continue this theorem. Part 3 of the theorem, or even continuation of part 2. That in this quiver situation, this algebra AGV, this quantization algebra, is a trunk. Well, okay. So maybe this is only exactly true if G is if this quiver is of finite type. And maybe I should also restrict to the case when mu is dominant. Although maybe thanks to Alex Weeks' recent paper, we don't need this restriction. But anyway, that this algebra here is isomorphic to y lambda mu, a truncated shifted Yang-in. And maybe you don't care that much about truncated shifted Yang-ins, but for example, in the if we started with the quiver which looks like this, in this case, then this AGV will be nothing but the universal enveloping algebra SLN modulo the ideal generated by the positive part of its center. Well, more generally, you can get other central quotients. The universal enveloping algebra of SLN there's a whole theory of this flavor group, which I didn't enter, which allows you to vary the parameters here, but let me not get into that. Okay. Then this last point here appears in the appendix to this BFN paper, which has many authors. I think that's correct. Okay.
Does A through B always have an action of the group G? In your example here.
No.
Not a G.
I mean in this quiver case, I mean there's this other group, the group I was calling GQ floating around. So yeah. The torus of that group acts. Does the group act? No, that group won't necessarily act, but it's torus, for example, will act. Okay, so I want to define modules for these Coulomb branch algebras using kind of Springer theory. So let me just maybe briefly recall the usual Springer theory, something about it. So in the usual theory, we consider the cotangent bundle of a flag variety, G mod B. So that's pairs G, and I'll write B prime. So B prime is sorry, that's not right now. X, B prime, let me write the other way around. B prime. Okay. I try to make it look better. Look more like what I was writing before. G and X. Okay. Where G is in the flag variety and X is in G of the standard Borel. Okay. So sometimes you might write a pair consisting of Borel and a nilpotent. Yeah. And sometimes you would write a nilpotent and a Borel subalgebra, where X is in the Borel subalgebra. And here I'll just to emphasize the similarity with what I was doing before, I'll write G and element the quotient, so which is obviously the same as well, not obviously, but it's the same as the space of Borels. And then we have the projection onto the nilpotent cone, and then we consider the Steinberg variety, which will be some triples like this: G1, G2, and X, where X is in N as well, and also X lies in G1B, G2B. And then in this usual Steinberg situation, you consider a nilpotent matrix, or point in the nilpotent cone, and you consider P inverse X, the fiber of this. This is a Springer fiber. And it's nothing but the set of all Borels which contain your given X. G's such that X is in GB. So the analog of this kind of picture in our situation is as follows. Well, obviously the analog of this would be to consider a space which hasn't yet appeared, but which is usually called TGV or something. So it would be this. So we're back now in the BFN situation. So this G will be a point in the affine Grossmanian. The V will be in. Which I'll just like this. V will be in here. Sorry, V will be in here. And then the analog of this condition would be just that V is in here. So I didn't. So compared with the RGV, I didn't impose that V lies in V over power series. Just that V lies in V over the Laurent series. Just like here, I don't impose that X lies in the standard Borel. And so with this definition of TGV, this TGV mapping to V of Laurent series is analogous to T star G mod B mapping to N. And you might ask, what about RGV? What's it analogous to? So RGV is analogous to something which you don't that often study in the usual Springer theory, but it's easy enough to study it, which is just, well, look at the space of pairs. Look at the set of pairs of like that, where G is in the flag variety, and X lies in both this in both the given Borel sort of and the standard Borel, and its nilpotent. So that kind of space, which is nothing but the union of the conormals to the Schubert cells. In the union of the conormal, so you could write something like this maybe. So that's the analog of RGB. And somehow the reason that we, in this BFN story, why we consider this sort of RGV and not this Z, the fiber product here, because you could study similarly this analog of Z, just take the fiber product of two copies of T over V of the Laurent series. The reason why is basically to avoid some infinite dimensionality problems, in particular to avoid having to work with equivariant cohomology with respect to the group of G of K, G of Laurent series. So that's why it looks a little different than the usual Springer theory. But nonetheless, we can still study it. So we're going to be interested in then in fibers of this map, because that's analogous to this map here, where we have our usual Springer fibers. So given C in V of Laurent series, we have study the BFN Springer fiber. So by definition, it's a set of points in the affine Grassmannian such that C lies in the lattice coming from G. So I call it F sub C. So it's a relatively straightforward guy. Okay. So let me state a theorem about it. So maybe just maybe just to some examples. Like one example you could imagine is taking C to be 0. In that case, FC is the entire affine Grassmannian. Okay? This example we're not going to consider much. In fact, you'll see in a second I'm going to do something which is going to rule out this example. Another example which you might imagine is you might imagine that this representation V could be just the adjoint representation. In this example, this FC becomes just the usual affine Springer fibers. This is also not a case I'm going to be interested in.
Taking C and B, they're not in the Laurent series.
That's true.
But it,
Yeah. No. Sorry. No. I mean, in this case, C is in G of Laurent series. That's.
oh, okay, yes.
And you get the usual affine Springer. So those are some cases that I'm not so interested in. Let me show you a typical example that I'm more interested in. Here's a more typical situation which I like. We could take C, so another example. 1, 2, 3. We could take our V just to be hom CK into CN, and G to be GLK. In other words, I just have this quiver. And then we could take, the choice of C doesn't actually matter very much, as long as, well, okay, let's take C to be actually in V, not in V of of k, but just actually in V. And then we assume it's injective. Okay. If I do this, then FC, well, it's a point in the affine Grassmannian of GLK, which means it's just a lattice in an O lattice in Laurent series to the K. And the condition, this condition here, just translates to that C, after I apply this injective map, that this C of L lies inside power series to the n, but that's actually just equivalent to just that L itself lies inside power series to the n. Sorry, power series to the k. So in that way, you see that the C didn't actually make a very big difference to the fiber. So in this case, this FC is just the positive part of the affine Grassmannian. Okay. Let's see some generalizations of this guy in a few minutes.
So will you always be in certain cases when the C is kind of constant?
No, not necessarily. Okay, now I state my theorem. So this theorem, so this is joint work with Justin and Alex. Okay, so the theorem is that if C is chi-stable, and so let me just so remember we had this chi, the character of G. This is the first place it really seriously enters. So this chi-stable means over the field of the Laurent series. I want that the map from G over the field of Laurent series to V cross A1 over the field of Laurent series given by G goes to G acting on C, comma chi of G to be proper. That's the stable. So if C is chi-stable.
You mean C viewed as an element of the cotangent bundle of V?
No. No, just in V. I don't think it will change it, but I don't think there's no need to invoke the cotangent bundle to make this definition. And has trivial stabilizer. This second condition we can relax a little bit, but just for simplicity, let me just state it like this. Okay. Then notice this rules out these two examples here. Then under these hypotheses, we can prove some nice properties about the Springer fiber and the resulting modules. Okay. So one. So okay. So each component. So in general, the affine Grassmannian of this group G will typically be like a kind of product of GLs, not a reductive group. So the affine Grassmannian will have maybe many connected components, and therefore FC will have many connected components. I mean, FC might even have more components than that, but let me just say that those components, by component of FC, I mean the intersection of a connected component of affine Grassmannian with FC. So each component of FC is a finite dimensional projective variety. Okay, so I don't have any like the stuff you have in here going on. Two, the homology of FC is a module, and this is just ordinary homology for ordinary Burrell-Moore homology. Oh, sorry, FC is compact, so Burrell-Moore and regular homology will coincide. Is a module for this algebra A, and if we put C star covariant, it'll be a module for the quantized algebra. If we don't put C star covariant for the ordinary algebra. And part 3 is this module lies in category O for AGV. So the choice of our character chi allows us to form, allows us to define a notion of category O for AGV, because the algebra AGV, let me just say it in words, will be graded by the connected components of the Grassmannian of G. And the choice of chi gives us a map from that set of connected components to the integers. And so that gives us an integer grading on the algebra and allows us to define a notion of category O.
Do you have any assumptions on chi here or not? For instance, do you want the Higgs branch to be smooth? Or
No, there's no assumptions.
And when you write A, it's with a loop rotation, it's quantized situation? Or
Yeah, quantized situation. When I write A0, I mean non-quantized.
When you write GK, there is a loop rotation or there is no? Is the, would you say the key stable?
No, no loop rotation.
So for example, chi trivial, there is no chi stability.
No, there can be still. There could be still. I mean, for example, if you took this situation but took the group SLN, I think then it's still stable.
But you need some impose some homogeneity relation and C.
No, but
Because
homogeneity.
it is not fixed by loop rotation or like this. Because there is loop rotation in A, so
You mean to get the action of the loop rotation? I forgot to detail this. It's a good question. I don't believe that it's necessary. The definition is sort of slightly indirect. So because of the definition of R, the definition of this module structure has to be somewhat indirect.
But just you have to justify somehow why loop rotation acts on the Springer fiber. So
Yeah, I mean even to define this thing. Okay, maybe
just to define the action itself.
Yeah, maybe that's a good question.
So if you see it's constant, there's no problem. But
Yeah, maybe that's a good point. Okay, I should think about that. Okay, a priori, let's say let's say we impose that it's constant if we want to get an action of the loop rotation. Okay. Or somehow right. Okay, maybe some example. So let me give some more examples. So suppose that my group is a torus, and so this torus acts on V, which is Cn, and it acts by some characters, a to 1, a to n, of this torus. And we can choose some fixed point, some point C that we're going to use, and I'll choose something like this. And we have to make sure we sort of have enough non-zero guys here to make it stable.
which is not constant.
Which is not constant. But it's kind of equivariant for this C star, so I think it will not.
Which system?
Okay, let me not worry about this C star. Okay, in this example, the Springer fiber. So in this example, the affine Grassmannian, we have a torus. So the affine Grassmannian is just a bunch of points. So we're just left with a set of set of points, which will be fine. Well, not necessarily finite, but we're left with a discrete set. So all those z mu. So mu here ranges over the co-weight of the torus. And then the condition that we're in FC is nothing but, well, it's this condition that C is in Z mu Z. And so that's this condition. Oh, sorry, I erased it. But the defining condition of being in the BFN Springer fiber is C is in G V of power series. So here it's written like this. And this is equivalent to a condition that a to I is greater than or equal to the pairing between, Ci is greater than or equal to the pairing between mu and a to I for I equals 1 up to p. So if you think about this condition is defining some polytope, possibly not finite, but some polytope, and this is just the lattice points in the polytope. And the algebra in this case, when we have a torus, the algebra is this hypertoric enveloping algebra, which was very well, its modules were extensively studied by Braden, Licata, Proudfoot, and Webster. And we can show that for various choices of C, you can produce sort of like, well, all or many of the interesting modules for this hypertoric enveloping algebra by this construction.
So you need only the orbit of C under the positive part of the group to be balanced on a rotation or something like that?
Yeah, it's probably something like that. The problem is that I probably messed up because I've simplified the statement of the theorem, because in general there's this flavor group going around, and the actual statement of the theorem has the flavor group in it, so this C star action is sort of buried inside the flavor group for us. So anyway, that's why.
Because A is equivalent homology, where the module is not equivalent homology. So you have to evaluate the equivalence in some way.
Yeah.
You need only FC, you don't need C, only FC needs to be.
Yeah, I mean, in general, we first prove that this is isomorphic to the cohomology of some other space, which does have an action of the group, and then that equivariant homology of that space.
It means that the quantum parameter information in A acts by a specific value. It is evaluated in its action to a non-trivial, I guess, value.
Not. Yeah, sorry, I haven't.
Yeah, you specialize the equivariant parameter.
It depends on but not the quantum parameter necessarily. If C is okay, if C is just a constant, then not. But if C is not,
No, but
let me.
you just require that if you apply loop rotation to C, that applies on G of O times C.
Yeah.
That would be.
Yeah, but I think we even have a more general version where you can lie in the flavor. So that's the same too. Okay, so another example of this affine Springer fiber, which is kind of really our motivating example, is when GV comes from a quiver. So in this case, let me take C just to be a constant element, so not of a Laurent series, just in V. So this C corresponds to a framed representation of the quiver. Framed just means I have this auxiliary vector space around, and I have also a map from those auxiliary vector space to my thing. So for example, maybe I have a quiver like this, and then I have some framing here. So C corresponds to a frame representation. And then let's examine what FC looks like in this case. Let me write M for the underlying vector space of my quiver, but just the circled vertices. So my gauge group is G, that's the product of GL and I's. So FC will be a points, I mean, it's a subvariety of the affine Grassmannian of this group G. Therefore, it can be considered as the lattices in k to the ni for each I. And so a priori, it's a collection of lattices Li. In Laurent series. Right. And using the fact that this representation is stable, I choose chi to be in the, just given by the product of the determinants. And using that, it's just the fact that it's stable, and using Hirako's previous work, we can prove that this L actually doesn't just lie in Laurent series to Ni, but actually lies in power series in power series. So I'll just write like M over power series. And then we have the additional condition that it's just a submodule CQ tensor power series submodule. So in particular, it doesn't depend on the framing at all, on the choice of this C. So this generalizes that example I said a few minutes ago, where we got rid of all this. We just had one thing. And then we had, well, the arrow is the other way, but it doesn't really matter. And then we just had this positive part of the affine Grassmannian showing up, and it didn't depend on the choice of that injective map. So similarly here, will not depend on the choice of the framing at all, and it's just the space of submodules of this module tensored with power series. And one, why I like this a lot is because
Sorry, wait, but it's also in so it's for this particular choice of chi.
for this
So
particular
therefore
choice of chi.
It will depend on chi, right? So it's
Yeah.
So you fixed out, I'm sorry, what do you, what's
Sorry? Q is the quiver. CQ means path algebra with a quiver.
but M is not, M is just a vector space,
Sorry, M is this vector space. I've fixed a point in this V. The choice of the point in V gives rise to a module structure, quiver module. This M becomes a module for the quiver path algebra. And therefore, M tensored power series becomes a module for the quiver path algebra tensored power series. And I'm just taking submodules of that module. It's just the space of all submodules of that module.
But where is the condition depending on C?
So the condition on so C is two pieces of data. One is the framing data, and the other piece of data is the module structure. And I'm saying the framing data doesn't matter. Only the module structure matters. So there's a kind of, well, not a hard theorem to prove, but it's not obvious statement.
This is the case where C is constant?
Yeah. And one thing that I like about this is because it gives us a way of taking this quiver representation, and we get a module, well, we get a module in this case for our A GV or for our A0 GV. And we know that these guys, spec of this is the affine Grassmannian slice. Spec of this one is the affine Grassmannian slice, and this is a truncated shifted Yangian. So we get, in fact, we can, in this way, we get a coherent sheaf on this affine Grassmannian slice. And in good cases, sometimes, this coherent sheaf will be actually, oh, maybe right here, sometimes, is actually the structure sheaf of some MV cycle Z. In general, not, but sometimes there will be. And this idea that homology of a space like this being the functions on some MV cycle, I mean, in particular, we would get from when this happens, then we have the homology of this FC is a coordinate ring of some open subvariety of some MV cycle. And this expectation, the idea that this should occur comes from related work that I'm doing with Pierre Baumann and Alan Kamnitzer. So based on considerations that have nothing to do with Coulomb branches or anything, we independently reached the idea that for some quiver representations, we should have such a equality like this. In fact, our expectation is it should occur for certain nice pre-projective algebra modules, not just for quiver representations. Okay. Yeah.
I'm going to formulate when this is
When you actually get an MV cycle.
yes.
No. Like the short answer to the question is that we expect this to be true if and only if the MV basis vector corresponds to this dual semi-canonical basis vector. And in fact, we found an example where they don't the two basis vectors do not agree, basically by somehow checking that this equality doesn't hold. And so we don't always expect to be true, but we expect to be true in sort of a large, for example, in on SL2, SL3, and SL4, it will always be true. Okay. So in the remaining time, I'd like to explain one more thing, which is the relation between these BFN Springer fibers and quasimap spaces. So let me recall something about quasimap spaces. So given the G and V that we started with, how much time do I have left? When do I have until? Quarter after, or?
Yeah,
Okay. Should be okay. So given this G and V we started with, we can consider maps from P1 to the stack quotient V over G. So that's pairs PS, where P is a principal G bundle. On P1, and S is a geoquivariant map from P to V. And we can consider what's called, well, I call it quasimap. So it kind of, although in this guise it just looks like a based version of this space. So I'll write it like just like this. So pairs like this. PS, such that I want that if I take S and evaluate it at infinity, by which I mean pick any point in the fiber. So this P is a principal bundle over P1, so I can look at the fiber over infinity. And I want that this infinity is sent to C. But effectively, I just mean that this infinity is sent to the G orbit of C. Sorry, C here is a constant guy. And maybe I can assume that this C is also chi stable. So just an example of this. If I take my simple example with Hom from Ck into Cn, and as usual, G is just GLK. Oh yeah. Well, C will be C will just be the standard inclusion of Ck into Cn. K is less than n. Standard inclusion. Although I could take any injective map really. Then this quasimap space will be nothing but pairs consisting of a locally, so here F is a rank K locally free sheaf in P1, which appears as a inside of the trivial vector bundle of degree n. But this map here is not necessarily inclusion of vector bundles, just the inclusion of coherent sheaves. But I also want the condition, related to this base condition, such that at infinity, this map is an inclusion of vector bundles, and in fact just corresponds to the standard, this corresponds, well, is just this usual inclusion of Ck into C. Okay. And more generally, or similar to this one, if we considered a quiver, the quiver related to the flag variety of type A as before, we take V to be this coming from the quiver like this one, up to n minus 1, and then with the framing of n, then this quasimap space has been well studied, and it's collections of locally free sheaves F1 up to Fn minus 1, where Fi is a rank I locally free sheaf. And they're all embedded into each other and ultimately embedded into the trivial vector bundle. And this space is called the Le Mans space. Good. Now, recall FC was elements in the affine Grassmannian, where C is in G of the V over power series, and we can write that as a triple P of phi S, where P is the principal G bundle on the disk. Phi is a trivialization on the puncture disk. And S was a section, or we can think of it equivalently as a map from P to V, such that on D cross it equals C. In fact, yeah. And in the usual way, if we have a principal G bundle on the disk trivialized away from the origin, we can extend it to a principal G bundle on P1. And then, because this section is just equal to C on this punctured disk, it will just extend to a section on all of that principal G bundle. So in that way, we get an embedding of this BFN Springer fiber into the quasimap space. And in fact, these two spaces will actually have isomorphic homologies. So we have an isomorphism between the homology of this quasimap space and the homology of our BFN Springer fiber coming from this embedding. And the idea of the proof of this,
What's the assumptions on C here?
just that it's constant and chi-stable.
And there was some.
I'm not
there was
actually
some
sure.
additional assumptions you made before, like
Trivial stabilizer too.
trivial stabilizer.
Yeah. Well, yeah. Maybe you can get away with a little bit less, but let's say that for now. Let me just explain a little bit the idea of the proof. So I explained that there was an inclusion of FC into this quasimap space. And this quasimap space actually maps down to a different quasimap space, which is actually an affine scheme. And it's the quasimaps also in some based from P1 into the quotient of V by the commutator subgroup G prime. So this is a here I use the affine GIT quotient, and here I mod out by take the stack quotient by G mod G prime, which is a torus. So this here is a torus. This here is a affine GIT quotient. And this whole thing I here is an affine scheme which is contractible. In this way, we prove that the homology here is the same as the homology here. So this generalizes.
You mean that you want to say that this FC is a fiber over 0? So
Yeah, and this FC is the fiber over this. This thing contains a 0 point, and this FC is the fiber over 0. And in this example of Le Mans space here, so when this is a Le Mans space, L nu or something, then this space down here will be a Zastava space, Z nu. So it's generalizing the familiar picture of the Le Mans space mapping to the Zastava space to this more general setting. And I guess this central fiber of this map from the Le Mans space to the Zastava space was studied in this old paper by Kuznetsov. But so this BFN Springer fiber is a generalization of that. Okay, I'll stop there. Maybe one last thing. Sorry, one important thing I just forgot is that on this Le Mans space, on the homology of the Le Mans space, there's an action of SLN or of the Yangian defined by Fagan, Finkelberg, Frenkel, and Rybnikov. And actually, it's not and so that's acting here. On the other hand, because of our BFN Springer Fourier, we have an action of the same SLN here. And it's not immediately obvious that those two actions coincide, but we expect they do. That's all. No need for more clapping.